First lesson, implicit differentiation. What does that mean? What is that? We'll talk about it. We've been dealing with functions so far. So x squared plus 2x plus 3. What does it look like? It's just a parabola. You get an x, plug it in, you get a y. I don't even know what this looks like. Something like this. I don't know. It could be shifted up, down. Just looks like that. Okay? And we figured out we could find tangent slopes of that. We could take the derivative of this, and what we'd get would be y prime or dy dx. I'll use dy dx a lot today, so we're going to switch it from y prime and say that's dy dx, and that's equal to 2x plus 2, which is great. And what I can do with that is any x value that gives me a y value of points, I could plug that x value into this derivative equation, say at 1, and find the tangent slope. Which means at 1, here's the tangent slope that is equal to 4. Something like that, okay? Well, functions are boring. Functions aren't fancy. There's so many other things out there, so many other different types of equations with really, really cool looking graphs that I want to look into, okay? So we're not going to work with functions this unit. We're going to deal with these implicit equations. Implicit equations are non-functions. And they have tangent slopes and they have concavity too. Let's show you some implicit equations that we're going to be dealing with. We have simple guys like circles. X squared plus y squared equals 9. A circle, right? This has tangent slopes. This has concavity. We can examine that. We could look at something like this, which we're going to take the derivative of in a little bit. And this is 1/3 y cubed plus 2y squared minus 5y minus x squared equals 4. And it ends up with a graph like that. And this has tangent slopes. And this has concavity, and we can examine that. If I change the 4 from a 4 to a -4, all of a sudden this graph looks like the thing that ends up in the back of your throat, which is pretty cool. I can have ellipses that are rotated. I can have just a regular ellipse. I can have all sorts of things. This is a curly Q. I'll show you the graph of this. X cubed plus y cubed equals 7xy. These are interesting graphs. These are interesting equations. Okay, and these are implicit equations, and we are going to take the derivative of these because we're going to find the tangent slopes of these interesting equations at points. Okay, so there's an implicit equation. It's just easy. It's not easy to plug in an x and get a y. Typically, you won't be able to solve for y and put it in terms of y equals and some stuff. You usually will have a plus or minus square root in this case. If I solve for y, some other equations with like y cubes and x cubes, and you just won't be able to solve for y. Okay, so it's just we keep it like this. Okay, and it's important. What we did up here, we took the derivative and we found dy dx. Okay. Finding dy dx when we're taking derivatives. We will do the same thing here. We'll take x squared plus y squared equals 9, and we need to develop some dy dx equation where I can plug in certain values and get slopes of tangents. Okay? I want to be able to find dy dx of this. Okay? Now, what did I do for the first one? I took the derivative with respect to x of both sides. Now, you probably skipped this. You probably just listed the derivative of as 2x plus 2, maybe last unit, or maybe when you're just quickly doing your homework. But the proper way to do it is to take the derivative of both sides of the equation, and the derivative of y is dy dx, kind of like multiplication, and then the derivative of the right side is that. Well, for this, I'm going to do the same thing. I'm going to properly take the derivative of both sides. Okay, and we're going to just take the derivatives like normal, only it's a little bit more complicated, just a little bit. Like the derivative of x squared, you know that's easy, that's just 2x, right? And the derivative of 9, let's write this really quickly, the derivative of x squared, that's 2x, easy. The derivative of 9, you know this one, that's 0. What do you think the derivative of y squared is? Right, 2y would be too easy, not 2y. Not 2y, something else. Turns out it's really, really close to being 2y. Really close to 2y. I'll show you exactly what it is and why it's really, really close, and you're going to be like, okay, this isn't that bad. Let's look at taking derivatives of other variables, y's in this situation, with respect to x. Okay? Let's start with the derivative with respect to x of y. What do we say that is? That is y prime or dy dx. We're going to just use dy dx in this situation. Why is it dy dx? Because kind of like multiplication, the d can be multiplied by the y. The dx kind of gets multiplied by a 1 if it's y over 1. And we say this is dy dx. Well, let's look at y squared. Now I'm going to do it a little bit differently. I'm going to treat it like a composition of functions. Okay? I'm going to put parentheses around y. And I'm going to use the chain rule. Okay? I'm going to say this is not just y squared, this is instead this function that is being squared with y inside of it. I'm going to say there's an outside, and you're used to this, of stuff being squared, and then there's an inside of that stuff. Okay? Just going to do it. It'll make sense in a second. We know the derivative of something being squared is 2 times that stuff to the first power, right? So I say this is 2 to the first, right? And we leave the inside alone. Take the derivative of the outside, leave the inside alone. But then we have to multiply by the derivative of the inside, right? Well, we just said that the derivative with respect to x of y is dy dx. So I actually have to put that as well. I'm going to do the same thing for this one and this one. I'm going to use parentheses. I'm going to say the outside is 3 parentheses to the 4th power. The inside is just the y. I'm going to say the derivative would be 12 stuff to the 3rd times the derivative of the inside, dy dx. We have a y in there. I'm going to do the same thing with 6y. I have like an outside, which is 6 parentheses, and inside, which is y. The derivative of 6 parentheses, or if it's the derivative of 6x, the derivative would just be 6 times the derivative of the inside, dy dx. Okay? So let's look at this. Derivative of y squared, 2y, and then a dy dx. The derivative of 3y to the 4th, 12y cubed, and a dy dx. The derivative of 6y is 6, and a dy dx. Taking derivatives of y's with respect to x is the same as taking derivatives of x's. Same procedure, same rules that you know. The only addition is that we have to multiply by a dy dx afterwards. Okay? Okay. You can write that down just so you don't forget it. Now, what's interesting, you don't have to write this down, you just kind of have to look at it. There's another way to take this derivative of x squared using the same procedure. Okay? If I turn this into a chain, I would take the derivative of the outside, leave the inside, and then multiply by the derivative of the inside x. Well, we could say that the derivative with respect to x of x is, using kind of this multiplication technique, dx over dx. What's dx over dx? It's just 1, which is why we don't list off dx over dx, and we just say the derivative of x is 1. Okay? Which is neat, but you could do it this way. Okay? You could do this with any variable. Just whenever the variables aren't the same, whenever this is x and this is something else, we're going to have this extra thing. In this situation, it's redundant. It's not necessary. But all of a sudden, if I took this and said, what is the derivative with respect to x of z squared? Well, it would be 2z, but then I need a dz dx, which is why it's necessary. Okay? But today we're just dealing with y's. Okay? So we're just going to deal with y's and x's, not z's. And the key that you need to know is the fact that you need to multiply every derivative of y by a dy dx. So let's go up to this. Turns out the derivative of y squared is 2y dy dx. Well, if I'm looking to find dy dx, there's a dy dx. That's going to help me. What I'm going to be able to do is algebraically solve for dy dx to have an expression, an equation, where it's dy dx equals something. Okay? I'll be able to subtract 2x divided by 2y. I'll get dy dx is equal to negative x over y. All of a sudden, I have this, a derivative with x's and y's in it. I will go over step-by-step procedure of how I got there. Right now, we need to practice taking derivatives of x's and y's so that we're ready to take derivatives of these implicit equations. Okay, so let's go and practice taking derivatives of x's and y's. Important thing to know when we have x's and y's or x's and y's and numbers is that the rules still apply. Okay. Okay? So if we have stuff being added together, well, this is the easiest rule. You just take the derivative of all of the individual pieces and add them together. Now, the derivative of y squared we know is 2y dy dx. The derivative of x squared is 2x. And that would be my derivative of y squared plus x squared. Okay? That one's easy. However, where people get tripped up, I'm going to actually change this, is if we have something like x times y. People a lot of times think that the derivative of xy is just y, because you think of y as like a constant, the derivative of x is 1, but that's not true. And that's because this is a product. So you need to use your product rule. So let's see what the derivative of x times y really is. Remember, we will have the first one we will denote as f, the second one as g. I'll take the derivative of f, which is 1 times g, plus the derivative of g. The derivative of y we know is just dy dx times f. Whoops, which is x. Okay, a little bit more intense than just y. Okay, and of course, if we had something like, and we could do this really quickly, 2x squared y cubed, it'd be the same procedure. Derivative of the first times the second plus the derivative of the second times the first. The derivative of y cubed would be 3y squared, included dy dx, times the first. Okay? Product rule. We could have a quotient. Don't forget to use the quotient rule. X over y. Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over bottom squared. Okay? Okay. Well, you guys take the derivative of this. See if we can get it. X squared plus xy plus y squared. Okay, it should be this, 2x plus y plus dy dx, x plus 2y dy dx. Any questions so far? Okay, good. Well, here we go. We're ready to implicitly differentiate something like x squared plus y squared equals 9, or something that ends up having a picture of an ellipse, thing in the back of your throat, all stuff like that. Okay? Here are the guidelines. Now, the guidelines are simpler than this. I wrote them out in terms of four steps, but really there's two. It's differentiate, and then 2, 3, and 4 is just solve for dy dx algebraically. However, you will find that every single time you solve algebraically, you're going to do the following procedures. You're going to collect terms of dy dx on one side, you're going to move the terms onto the other side, you're going to factor out dy dx, you're going to solve for dy dx, and this is going to be by dividing. Okay, now let me show you quickly with this first one how it's done, but the next example we're going to do is a more realistic example of something you'd see. This one's going to be really easy. Okay, so x squared plus y squared equals 9. Step 1. Take the derivative with respect to x of everything. Make sure you do both sides of the equation. Don't forget the right side. Everybody forgets the right side. We take the derivative of x squared, it's 2x. The derivative of y squared, 2y dy dx. The derivative of 9 is 0. Now the rest is just solving for dy dx. How are you going to solve? We got to isolate it. We're going to move the 2x first by subtracting it. We'll keep the 2y on that side with the dy dx. Then I can just simply divide by 2y. I can simplify the 2's, and I get dy dx equals negative x over y. Okay? Now, this is going to be great. However, this is different than what we're used to. We're used to having derivatives that just have x's. Okay? And what we could do is just plug in an x, and we'd get a derivative, a tangent slope. This is not so simple, and it's good that it's not so simple, because we have x's and y's, which means we are going to have to plug in a point, both an x and a y, and the point has to work in my original function, it's not a function, my original equation, to find my tangent slope. Now, That means I can't just plug in a random point like 4, 1. That's a random point. 4, 1 is not going to be able to be plugged in here because 4, 1 is not a point on this original equation. I plug in 4 for x, I get 16 plus 1, 17, not equal to 9. That's not something I'd plug in. But I would plug in things that would work. Give me an example of a point that works. I just heard something. What was it? 3, 0, right? So what I can do, since I know 3, 0 works, I can find the slope of the tangent of this at the point 3, 0. Well, I plug in 3 for x and 0 for y. I get an undefined tangent slope. Well, that's confusing. What does it mean to be like an undefined tangent slope? Vertical, exactly. An undefined slope is a vertical slope. Well, let's look at the graph of x squared plus y squared equals 9. Look at the point 3, 0. What do we have? A vertical tangent slope. Fantastic. We now have the capabilities of any point finding the slope of the tangent to that original equation. Let's take other ones like 0, 3. We know that works. 0 squared plus 3 squared is 9. Well, I plug in 0, I get negative 0 over 3. That's just equal to 0. I look at the graph. At 0, 3, I have a horizontal tangent. Fantastic. I can take any point that works, something that is, close to a certain location. Maybe let's talk about root 4, root 5. We know that works. Root 4, root 5, it'll be the opposite of root 4 over root 5. It's going to be close to 1, but it's negative. If I look at that point on the graph, root 4, which is 2, and root 5, which is a little bit more than 2, right here, slope of the tangent, close to negative 1, which is great. I feel like the air conditioning just turned off. Okay, so we understand what we can do with these. We plug in points to find the tangent slopes. Let's keep going, even though it's hot in here. Okay, here is the next equation we are going to take the derivative of. 1/3 y cubed plus 2y squared minus 5y minus x squared minus 4. We're going to do a bunch of different problems that could be asked of you for this. First problem that could be asked of you is just to find dy dx. Let's go. Step 1, take the derivative with respect to x of both sides. Don't forget to take the derivative of the right side. Don't forget to include dy dx's after the derivative of everything with a y. Okay, step 2. We are going to solve for dy dx. Now, that involves 3 minor steps in that. First, move everything without a dy dx attached to it onto the other side. That's kind of the first minor step on solving. Step 2, Factor out the dy dx. After you factor out the dy dx, you will notice that you'll just have a product. Dy dx times some stuff. Step 3, solve for dy dx. How are you going to do it? Well, this is a product, so to get rid of the y squared plus 4y minus 5, you divide both sides by that stuff. Okay, good. That's the first type of question you will encounter. Second type of question you will encounter is to find your slope at a point. If I look at my original equation, I know the point 0, 2 works. Let's find, sorry, not 0, 2, 2, 0. 2, 0 works. Let's find the slope of the tangent to this function. This is the, not function, this equation. This is the equation, looks like the thing at the back of your throat. Right there, okay? Let's find the slope of the tangent at this point 2, 0. What do we get? Exactly, -4/5. We plug in both the x and the y, we get 4 over -5. And then, if I have Wolfram available, I look at the slope of the tangent and I realize that that slope is negative and it's close to -1. Down 4 over 5. So that should make me feel good. Okay? So that's the second type of question that's going to be asked of you. Another type of question. Yes? Right, well, there will be other points that you will talk about. The great thing about non-equations is that, 2 actually goes with, it looks like +2. If I plugged in +2 here, 8/3, it's actually not going to be +2. But there is some value for y that'll make these three things 0, where I'll plug in 2 and that'll work.
Oh, so that's why we have a 2-point simplification now instead of a 1-point simplification.
Exactly. Because there's multiple places that it could be. We will have both the x and the y points, because if I just say when x equals 2, well, that would kind of assume that you would have to find the y here, here, and here, and then find your tangent slopes at those locations. And we're not going to do that often. You might be, but it won't be that difficult. You can't do it for this equation. It'd be too hard. Okay? And that's also why our derivative has x's and y's, because it needs both an x and a y location to get a specific tangent slope. Okay? 3, you might be asked to find the locations of your horizontal tangents. Let's just find our x locations. Okay, you might be asked to find when your x or your y's have horizontal tangents. I'm sorry, when your function has horizontal tangents at just one variable, either your x's or your y's. Horizontal tangents are when? The derivative equals 0, right? Well, I have a fraction for my derivative. If I have a fraction for a derivative, what do I need to do to set the derivative equal to 0? What do I have to worry about? Just what? Just the numerator. Great. So I just have to set 2x equals 0, and I get when x is 0. Okay? So, now, in this situation, we could try to find the y's and the points. But if I try to find the y's in my original equation, it's going to be very difficult. I'd have 1/3 y cubed plus 2y squared minus 5y minus 0 equals -4. You're not going to be able to solve that by hand. Okay, which is why the question will be designed so that you can do it by hand. In this situation, you find that when x is 0, if you look at your graph, when x is 0, here is your horizontal tangent. Good. Now, let's do one more question, which will be asked of you, is to find the locations, and let's find your xy locations of your vertical tangents. Now, we haven't had vertical tangents. These functions don't have really vertical locations. They do sometimes when it's just at a certain point. But typically they don't. Okay? So for a vertical tangent, we're going to have to set our derivative equal to being undefined. And when I set something equal to undefined, if it's a fraction, what do I have to worry about? The denominator. So I got y squared plus 4y minus 5 equals 0. I'll be able to factor. And get two y locations. Okay, now I get two y locations, I check on the graph, and I find, yep, when y is -5, here's a vertical tangent, here's a vertical tangent. When y is 1, here's a vertical tangent, here's a vertical tangent. Now, they ask you for the xy locations. So just answering the y's are not enough. We have to take those y locations, plug them back into my original equation, and I'm going to have to find the x's. So let's do that. I'll do that. Let's just do it for 1 because that'll be easy to do. We'll need that, and we'll need this. Good. Okay. So let's just say for y equals 1, we'll focus on, well, when y is 1, we'll plug 1 into our original equation. We'll get 1/3 plus 2 minus 5 minus x squared is equal to -4. I will then solve for x. So this is -3 minus x squared equals -4. This is -9/3, so this is -8/3 minus x squared equals -4. This is -12/3 plus -8/3 will be -4/3. This will be x squared is equal to 4/3, or x is equal to plus or minus √4/3. So I now have two locations, √4/3, comma 1, and -√4/3, comma 1, where I think I have vertical tangents. √4/3 is very, very close to 1. -√4/3 is very, very close to 1. If I look at my graph, we have points really, really close to 1, 1, and -1, 1, where we have vertical tangents, right here and right here. Okay? Those are all the types of problems that we will see, that we will be doing, that are complex. They involve a lot of work. Look at how much work I had to do just to find the other half of my answer. Okay? These problems all involve and all need to be, you need to be very careful while you're doing your work. You need to show all your work, and you need to be neat and organized. So first type of question, let's do it for this one. Let's just find dy dx for this. This is a rotated ellipse. Why don't we just find its derivative? Go. remember the product and the product rule. Remember the derivative of anything with a y will include a dy dx. Remember the derivative of y is just dy dx. Then move everything without a dy dx onto the other side. Factor out a dy dx, divide to solve. You will find a lot of your derivatives are going to be eerily symmetrical. Okay? And that should make sense if you think about our equations. This is like a rotated ellipse. Like our derivatives at one location are going to be the opposites of a derivative at kind of like the corresponding location, or the same as the derivatives of the opposite side of your ellipse. It all depends on you know what it looks like. Don't be afraid if you see your derivative looking like this. Right, just be very careful while you're doing your work, and you got that. Any questions about that? Yes? No. No. It's just when I have a lot of stuff, I usually use brackets just so I know it's a lot of stuff. I'll use brackets, assuming that I could have parentheses inside of the brackets, you know? Kind of another way to just distinguish. Just notation, making things orderly. Here, you can find this. Find dy dx. My advice is to include the 7 with the x. That way you don't have parentheses. When we have parentheses, we will deal with, we will have difficulty, you know, solving for dy dx after we take the initial derivative. If you had the opposite of my answer everywhere, fine. You just had this times -1 over -1. It just means you have your dy dx's on the right side, and you have the other stuff on the left side. And if you have a situation like that, totally okay. Any questions about that? All right. We're not going to do this entire problem. I'm going to come back to it, but this is the second type of problem. finding a derivative at a specific point. Turns out the point 3, 1 works in this original equation, so we can find the slope of the tangent at 3, 1. Now, here's the key. When you take the derivative of this, you might be thinking, oh, I'm going to use the chain rule. It's 3 stuff squared on the outside, and then x squared, y squared on the inside. And watch what happens. Using the chain rule, I'd get 6 x squared, y squared to the first times 2x plus 2y dy dx equals, the derivative over here would be derivative of the first, which I would say is just 100 if I include the 100 with the x, times the second plus the derivative of the second times the first. Okay? Now, because I have parentheses, it is not easy to manipulate this and to move the 2y dy dx on the one side and just move everything else. It's not. If I try to divide by 6x squared plus y squared, well, that will just trap the dy dx on this side. Okay, so all of a sudden, solving is a little bit more difficult. What you would have to do, and you could do this if you wanted to, is distribute everything and get rid of the parentheses. Which looks nasty, right? Well, you could, instead of distributing now, just have simplified the original. Try not to use a chain rule. Simplify first. So we'd have 3 times x to the fourth plus, that'd be 2 x squared y squareds times 3 would be 6 x squared y squareds plus 3 y to the fourth equals 100 xy. Take the derivative of this. And it'll be easier to solve for dy dx. Both ways, though, still do involve a lot of work and a lot of steps. Okay? So I will do this on the video. Last problem we are going to start are the xy locations of the horizontal and vertical tangents to this. I will also finish this and show this on the video. Okay? A couple extra examples are going to be on the video. I'm going to stop right now.